All in today's lecture we will talk about single phase transformers. The main outlines of the lecture are basic construction, theory of operation of transformers. Then we will deal with the ideal transformer with no losses by neglecting transformer losses. Then we will take into consideration the transformer losses for the real transformer equivalent circuit. After that we will talk about voltage regulation, then the two tests performed on transformers to obtain transformer parameters, which are the open circuit test and short circuit test. Last but not least, the transformer efficiency. First, we need to know what is a transformer. A transformer is an electrical device that converts AC voltage to another AC voltage level at the same frequency. It can step up or step down the voltage according to the application. It consists of one or several coils. It can be one coil for auto transformers or several coils for two-winding transformer, or more than two coils warped around a common ferromagnetic core for the passage of flux from the primary winding to the secondary windings. These coils are usually not connected electrically. The connection between the coils is through the magnetic flux. However, they are connected through the common magnetic flux confined to the core. The common flux that passes through the core from the primary to the secondary side. What is the working principle of transformer? The transformer working principle depends upon Faraday's law of electromagnetic induction, which states that mutual inductance between two or more windings is responsible for transformation action in an electrical transformer. Or, in a different way, the induced EMF or the back-induced EMF, according to Faraday's law, is proportional to the rate of change of magnetic flux with time, d phi by dt, or directly proportional to the rate of change of flux linkage, d lambda by dt, where the flux linkage is equal to number of turns times the magnetic flux in the core. The rate of change of flux linkage with respect to time is directly proportional to the induced EMF in the coil. The basic theory for a basic transformer is when we apply alternating current from the source, here is the source, to an electrical coil, which is the primary coil, which is connected to the source, flux will be obtained surrounding the coil, which is the flux lines shown in the figure, confined through the primary winding. If we get another coil nearby the first coil, there will be an alternating flux linkage with the second coil. The flux will link from the primary coil to the secondary coil. As the flux is alternating, it has a rate of change, or a rate of change of flux linkage with respect to time in the second coil, and EMF will be induced according to Faraday's law of electromagnetic induction. This is the most basic theory of a transformer operation. But is that basic transformer ideal? No. Because air has high reluctance, and the reluctance is a resistance to the flux passage through the material. Therefore, the above mentioned form of transformer is theoretically possible, but practically impossible, because open air in open air, very tiny portion of the flux of the first winding will link with the second coil. Only a small portion of the flux from the first coil will pass to the second coil because of air resistance to flux passage from the first coil to the second coil. Therefore, there will be small amount of flux and the voltage will be very small and difficult to measure. So we are desired to make the flux linkage almost all the flux produced by the primary winding. So the secondary winding, we need all the flux from the primary winding reach the secondary winding, or the flux linkage is 100% from the flux obtained or produced by the primary winding. This is efficiently and effectively done by placing a low reluctance path common to the both windings, or to the primary and secondary winding. We have this core. This material is a ferromagnetic material that can confine and integrate and collect the flux lines which are produced by the primary winding and pass it all to the secondary winding, so all the flux produced by the primary winding will be linked to the secondary winding. This low reluctance path is called the transformer core, through which the maximum number of flux produced by the primary is passed through the linked to the secondary winding. What are the main construction parts of a transformer? The main parts of transformer are the primary winding, which produces the magnetic flux and is connected to the electrical source. This is the primary winding, which is connected to the electrical source and is the source of the magnetic flux that will be passed through the core and collected at the secondary winding. The second part is the magnetic core of the transformer. The magnetic flux produced by the primary winding will pass through this core, which is this core. All the flux produced by the primary winding is passed through this path to the secondary winding and linked with the secondary winding to create a closed magnetic circuit. The magnetic circuit must be closed like the electrical circuit. Therefore, the flux will pass in a closed path, which is the core. The last part of a transformer is the secondary winding. The flux produced by the primary winding passes through the core and link with the secondary winding, which is the secondary winding. This winding is wound on the same core. This winding is connected or warped around or wound around the same magnetic core and gives the desired output of the transformer, which is the output voltage needed by the electrical load at the secondary terminals. There are two shapes of the transformer core. One is the core type transformer, where the coils, one is connected at one side, which is the primary winding, and the other is on the other side of the core. And the second type is the shell type. For the shell type, both the primary and secondary windings are wound across the same leg, which is the center leg, and are warped or wound over each other. For the shell type, there will be low stray flux or leakage flux, which leak from the magnetic pulse, while for the core type, the value of the leakage flux is higher as the flux can pass in this way or this way and leak from the magnetic path, which is the main path for the flux to connect the rotor to connect the primary and secondary windings by the maximum flux or flux linkage. For the transformer core material, the transformer core is made of silicon sheet laminations. These are sheets of silicon sheet steel. The main advantages of silicon sheet steel is minimum core losses, lower eddy current and hysteresis losses, no aging properties, longer lifetime, and high permeability, which increases the flux line that can pass through the material. It's a measure of the easiness of establishment of flux lines across the material. As the permeability increases, the number of flux lines will increase inside the material. There are two methods for winding wound methods or wounding the winding across the core. The first one is isolated winding wound directly on the core. This is for moderate voltage ratings. For moderate voltage ratings, we can place the isolated windings directly on the core. For high voltage, high power transformers, the coils are wound around a form made of plastic and then assembled over the core in the part where it will be connected, either for the core type at both legs, right and left legs of the core, or for the shell type at the center leg of the transformer. As the transformer winding draw current from the primary and the supply current to the load at the secondary, the passage of current will produce a heat energy in the windings and in the core. Therefore, we need methods of cooling the transformer. For low power transformers, natural air circulation may be enough. We can use the circulation of air around the transformer to transfer the heat from the transformer body to the surrounding. For high power, high rating, natural air circulation is not enough. We have two options or two ways. The first way is forcing air through core and winding by using a fan, or transformer can be immersed in transformer oil for cooling and for isolation, with a storage tank, generally cooling fins. The cooling fins or the outer surface of the transformer having cooling fins may be welded to the body of our tank to transfer the heat from the inside of transformer to the outer medium. Now we will deal with the ideal transformer, which has no losses. We have the primary winding, which is connected to the electrical source with voltage V1. The passage of current through the primary coil will produce an induced EMF E1, which is equal to N1 d phi by dt. The passage of flux through the core will link to the secondary winding with number of turns N2 and produce another induced EMF E2, which is equal to N2 d phi by dt. We can get the ratio between E1 and E2 by dividing N1 d phi by dt by N2 d phi by dt. d phi by dt will cancel d phi by dt. Therefore, the ratio of voltage equals the ratio of the number of turns of the primary to the secondary. The turns ratio N1 over N2 is called A, or turns ratio. As we are dealing with ideal transformer, then the input power will be equal to the output power, and we are talking about the apparent power, which is measured in volt ampere or kilovolt ampere, megavolt ampere. Therefore, we we have S1 equals S2, S1 equals E1 I1, and S2 equals I2 E2. Therefore, the ratio of the current I2 over I1 will be equal to the ratio of N1 over N2 and equal to the ratio of E1 divided by E2. Then the ratio of current is the opposite, or the reciprocal of the ratio of the voltage. The voltage is E1 divided by E2. For the current, the ratio will be I2 divided by I1 and equal to N1 over N2, or the turns ratio A. For the ideal transformer, if we have sinusoidal varying applied voltage, the magnetic flux will be also in the core will be also varying sinusoidally under ideal conditions. If the flux in the core at an instant of time equals phi maximum sine omega t, where phi maximum is the amplitude or the maximum value of the flux, and omega equals is the radian or the angular frequency in radians per second, equals 2 pi f. 2 pi times the frequency in hertz is the angular frequency. Then the induced EMF in the primary will be equal to E1 equals N1 d phi by dt. We take the equation of phi and differentiate it with respect to time. We obtain E1 equals N1 omega phi maximum cosine omega t. The differentiation of sine, we obtain cosine omega t times the derivative of the angle, which is omega. The above equation can be expressed in the phasor form, or we obtain the RMS value of the voltage, which will be equal to the maximum value, which is the part multiplied by cosine omega t divided by root 2, as this is a sinusoidal wave form. Then we divide N1 omega phi maximum divided by root 2. We obtain 1 over root 2 times N1 omega. We will substitute omega by 2 pi f times phi maximum. 2 pi over root 2 equals 4.44 times N1 times frequency times phi maximum. This is the general equation for the RMS value of the voltage E1. For E2, we will obtain the same shape or the same form of the equation, except for N2 instead of N1. As this transformer is ideal, therefore the applied voltage will equal to the induced voltage across the primary winding, and for the secondary voltage will be equal to the voltage of the load V2. What are the main assumptions considered for an ideal transformer? First of all, ideal transformer is an imaginary transformer. It is not a practical transformer, it cannot be existing in the real life, which does not have any losses, no core losses, and no copper losses, I square R, and any other losses inside the transformer. This means that the windings of the ideal transformer are purely inductive. We have neglected the resistance. The resistance will be equal to 0. Therefore, I square R losses in the coil will be equal to 0, and for the core of transformer is free of losses. The second assumption for an ideal transformer is no leakage flux or fringing. The leakage flux, which is the flux that pass through air and do not pass through the material or the core material. Therefore, we assume that there is zero leakage reactance of transformer, as we represent the flux with an inductive reactance. Whenever we place a low reluctance core inside the winding, maximum amount of flux pass through this core, and that does not guarantee that no part of the flux does not pass through this core. We have a part of flux that can pass through the air, which is the leakage flux. The flux does not take part in the transformation. This part of flux does not take part in the transformation action of transformer, and the flux is called the leakage flux of transformer. Efficiency of the transformer is considered as 100% as it has no losses inside it. The application of transformers in real life: we have transformers in generation. In generation stations, we generate power at a level of 30 kilovolt. Then we need to transmit this power for long distances. Then we have to step up this voltage to a level of 500 kilovolt. Then for distribution purposes, at the beginning of cities, we have to step down the voltage to lower levels, 44 kilovolt, 4.6 kilovolt, then to 120 volt. This for the American system of distribution. Generation of electrical power at a low voltage level is very much cost effective, as the current will be high at a high level. This high level of current, we have to step the voltage up. The voltage must be increased to reduce the current, so that I square R power losses, copper losses will decrease. The cross-sectional area of the conductors will decrease also as the current decreased. The capital cost of the system for the conductors and the structure that can hold these conductors for transmission, the towers, will be reduced, and an improvement in the voltage regulation due to a decrease in the voltage drop across the lines. The low level voltage must be stepped up. In this case, for an efficient electrical power transmission, we raise the voltage to decrease the current, so we have the previous advantages of reducing the current. This is done by step-up transformers at the sending end or at the generation stations. As this high voltage for transmission, we need to distribute to consumers directly. That cannot be done, as the high voltage cannot be distributed to consumers directly. We must step down the voltage level to a desired level at the receiving end at the beginning of cities, and with the help this is done with the help of step down transformers. We will be done now for this part until the ideal transformer. In the next part, we will talk about the real transformers.